very well, precisely written.
What I really enjoyed coming out of that calculation, that was so satisfying, was showing that you can gather gauge invariant degrees of freedom,
Yes.
and that the number of the you have two dynamical degrees of freedom, and then several that are kind of non-dynamical, and that was very satisfying.
The major issue is that a lot of people don't realize that everything in X mu nu is not a. Something more concrete.
Indeed, yeah.
In terms of joint research or
Absolutely.
something like that with
Yeah.
my team.
Yeah, yeah.
Your department.
Yeah,
and
absolutely.
his department.
Yeah.
So we can explore.
I actually, my department head is actually Bengali American. He spends a lot of time in Kolkata.
Okay.
So, yeah.
Okay, good.
Yeah,
so we can, tie up these loose ends.
Indeed,
and see if we can
indeed. He's one of
come
my
up with
best
something
friends,
concrete.
a guy named
Yeah.
Deepo Chakrabarti, and so
Okay.
he visits here a lot.
Okay. So see you again.
Okay, thank you.
Okay, so very warm welcome to all to this fifth AKR Memorial Lecture. Before we start, I will request to you all that please switch off your mobile phone or keep it in silent mode. This is a request to all. Okay. Now we are extremely happy to have with us Professor Scott. Um, we all know that physics is a subject which is driven by experiment. And there are very rare theories in physics where the theory came first and experiment came later. General relativity is one such experiment. And we are extremely happy to have Professor Scott with us, that who is among those theoretical physicists who actually told the experimentalists that if black hole binary at all exists, then what should we look for? And we are very much happy to have Professor Scott with us. Now this session will be chaired by another eminent theoretical physicist from India, Professor Shayan Kaur. Let me introduce him. So Professor Shayan Kaur is from IIT Kharagpur. He did his masters from IIT Kanpur, and also he
Can you do the
continued for
okay? I
and
can't seem to
Kanpur
get the
for his
okay to go away.
PhD. After that, he has done a couple of postdocs at Institute of Physics and IUCAA before joining IIT Kharagpur. Professor Kaur has done a great deal of work on Amal Kumar Raychaudhuri or Raychaudhuri equation, and this is for the young students that if you don't know that what AKR did, you can search archive, or you can also look at Resonance, that is the Journal of Science published by Indian Academy of Science, where you will be able to find some pedagogical level reports or articles written by Professor Sankar and also written by Professor Sankar and Professor Soumitra Sengupta on the Raychaudhuri equation. Okay, so without further delaying, let me hand over the session to Professor Sankar.
Okay, thank you for inviting me, and it's always a pleasure to be here at Presidency. I've been here many times, and particularly today because it's the day for the 5th AKR Memorial Lecture. Professor Amal Kumar Raychaudhuri, more known as AKR among students, is remembered through this lecture at Presidency every 2 years. Professor Raychaudhuri is famous for the Raychaudhuri equation, as all of you know, and he's also famous because he was here at Presidency and he taught and inspired generations of students for close to 3 decades at this very university. So that is why we are grateful to him and we should remember him. And it's particularly important for the younger generation to remember him every year, at least. So today we are very fortunate that we have Professor Scott Hughes as a speaker for this 5th AKR Memorial Lecture, and I know that everyone is eager to listen to him, so I will not spend too much time telling you in detail about his biography, because biographies are all there. You can just switch on your phones and you know who the person is. There is no point in spending too much time telling you about the person. But still, I have written down something, I'll read it to you. So, Professor Hughes is currently Margaret MacVicar Faculty Fellow at MIT, and it's a title which honors MIT's best teachers. So, this is important. Professor Hughes attended Cornell as an undergraduate, earning a BA in physics in 1993. He received his PhD in physics from the California Institute of Technology, working with Professor Kip Thorne, and then did postdocs at Illinois, Caltech, and at the Kavli Institute for Theoretical Physics before joining the MIT Physics faculty in January 2003. So let me read out some of his honors. In 2016, he received the Wigner Outstanding Advisor Award, MIT Physics. In 2012, he was made American Physical Society Fellow And I'll read out the citation, which is very important because this tells you about what he's done in research. It says, for pioneering work in gravitational wave physics, including modeling the waveforms of extreme mass ratio in spirals, you'll hear about it in this talk most likely, developing a framework for testing black hole spacetimes and showing how gravitational waves can be used to study structure formation and measure cosmological parameters. So this summarizes his work in a beautiful way. He also became John Simon Guggenheim Fellow in 2012, and earlier in 2005-06, he won the MIT School of Science Prize for Excellence in Undergraduate Teaching, the NSF Career Grant, and the Buechner Teaching Prize, MIT Physics. In 2004, he was appointed Class of 1956 Career Development Professor. So let me just end by mentioning that I am someone who always uses his review of 2005 when I teach gravitational waves or introduce gravitational waves. It's a review written with Jana Flanagan. It's wonderful, and I recommend that every student who wants to get started with gravitational wave physics should read that, because anything else, like MPW, may be very intimidating, but this is precise, clear, and beautifully written. So with that, I hand over the floor to Professor Scott Hughes.
Okay thing,
Yeah, let me get rid of that okay thing.
Can't we?
So the problem is now the system is, so my Keynote and Zoom are not playing together very nicely. Sorry, everyone, we're having slight technical difficulties here with the Zoom plus my laptop.
Oh, it's just the okay, right?
Yeah, but I don't have a cursor.
Oh, you don't have a cursor, so I have to check.
Yeah, I think I need to leave the meeting in order to.
Actually, it shares on a different screen, so you have to drag your cursor out of the.
Oh, you know what I should do is move this into the same screen as the browser. Okay. Now I need to go back to this link.
Yes.
Okay.
Recording in progress.
Yeah.
Okay.
Okay, let me just check one thing, make sure the sound is still going to the right place. That came out of my speakers. Where's my system settings?
Is it on another screen?
Yeah, I think it is. There you go. Okay, so that is output there. Good. Okay, let's go back to this. Go to share. Go to my Keynote. Share.
Then hide video panels.
Hide video panel.
Hide.
Hide floating meeting controls. Play.
Yeah.
Continue to share. If that's the worst thing that happens, I'm going to count myself lucky. So thank you all for your patience. And I must say that it's been a tremendous honor to be invited here. So Chaitanya made a comment about how I might be getting tired of hearing everyone thank me. To be perfectly honest, it's a little overwhelming. I've been an admirer of the work of Professor Raychaudhuri for many, many years. And so being here, being able to speak in his honor and to tell you about the work that really is the center point of what excites me in my career is kind of amazing. So let me begin. My talk is largely going to be about what we have learned about black holes from gravitational wave observations, but I want to tell you how it is that the famous equation of Professor Raychaudhuri is going to really help us to understand what is going on in all this. And so I want to go back quite far. Let's do a simple party trick. I throw a ball, it goes up and it comes back down. The harder I throw it, the higher it goes. And so that makes a question. How hard would I have to throw this ball? It's actually a plug converter, but let's imagine it's a ball. How hard would I have to throw this ball in order for it to never come back down? Now, obviously, I couldn't do it in here because I'd hit the ceiling, but if I were outside, this would be the question that I would pose if I wanted to calculate what's called the escape velocity. I would need to give the ball enough kinetic energy to overcome Earth's gravity, Earth's gravitational potential entirely? And it's a very simple question. This is something that students learn how to calculate. It is a first-year undergraduate when you study physics. And you get a result that for the Earth turns out to be about 11 kilometers per second. In other words, 40,000 kilometers per hour, which is a little bit slower than you travel on most Indian highways, as near as I can tell. The result, importantly, scales proportionate to the mass of this planet and to the size of this planet. And so if we look at it, for all the other planets in our solar system, the numbers are a little different, but they're similar. If I do it on the moon, 2.4 kilometers per second, Mars is 5. Jupiter and the sun don't really have surfaces, but if I go to what I can sort of define as their surface visually, I would get about 60 kilometers per second for Jupiter and over 600 kilometers per second for the sun. These last two numbers really seem large, right? Well, I'm a relativity theorist. And so for me, these are all small, because whenever I look at a number, I immediately compare it to the speed of light. So all of these numbers, to me, I look at them, and none of them even come close to 1% of the speed of light. All the escape velocities, to me, are slow. So that begs a rather interesting hypothetical question. What if there existed a body whose escape velocity, the escape speed, was the speed of light? So if I take that formula for the escape speed and set it to the speed of light, and then I just solve for r, what I find is that this hypothetical body just must be something that is extremely compact. I fix the mass, and then the radius is just determined by multiplying by Newton's gravitational constant and dividing by the speed of light squared. If I do this for m being the mass of the sun, this radius will turn out to be, there's a typo there, this radius should be 3 kilometers. I don't know why I wrote 1.5. Sorry about that. If I set it to the mass of the Earth, it's actually less than a centimeter. This calculation that I just went through with you was first done in 1784 by an English reverend. He must have been bored in between sermons every Sunday because he studied many, many things. He published articles on magnetism, on geology, on seismology, and he published on what we now know to be black holes. He did exactly that calculation that we just performed, demonstrating that if you made a body of some fixed mass sufficiently compact, it would trap its own light. He even published a letter in the Philosophical Transactions of the Royal Society that said we could have no information from sight regarding these objects, but we might still, perhaps, from the motions of luminous bodies near them, infer their existence. Hold that thought, because that's going to turn out to be a remarkably prophetic thing that he wrote. Again, I say in 1784. It's interesting for us to look back on this now in the early 21st century and admire it. His contemporaries didn't think so much of it. And in his biography of him, written in the late 19th century, his life was summarized with the sentence, he spent his final years vainly speculating on the influence of gravity upon light. Fair enough. Based on what we knew before the 20th century, gravity had no effect on light. And so, it was an interesting curiosity. Turns out, though, he's going to have the last laugh. Okay? And to understand how we know that, we need to go through how we've come to understand gravity over the course of history. So, to me, when I think about how humanity has learned about gravity, I begin with the first hominids who went outside, looked up at the sky, saw points of light. Some of them had the same position from night after night. Some of them moved. Clearly, that sparked a curiosity that I think has helped, I think, awaken what is latent in the human mind that brought us all into this room here today. But in terms of what has been written down that we know about from people learning about this, the first known codification, at least in European history that I'm aware of, comes from the Greeks, who divided these points of light into the asteria, the stars, and the planetes, the wanderers, we call the planets. This was written down and codified by Ptolemy in the Almagest. And what this did was it set out a picture of the universe that was really dogma after he wrote it down for quite a long time. It told us that the Earth was at the center of the universe and that the stars resided on a giant crystalline sphere that we could all observe. The planets were taken to live on additional sort of sphere-like structures that moved in the sky in occasionally reverse position. They moved in what we called epicycles. These days in science, whenever someone has constructed a model that's really baroque and it's got weird features, people will say, ugh, you're just putting in epicycles. We use this as almost a sneering term. But I want to emphasize something. if your goal is just to develop a framework that explains your data, here's the motion of Venus taken from a particular point on the Earth's surface at roughly the same time every night. That's an epicycle. You can see how somebody might say, you know what, this explains the data. And that's really, at the end of the day, what science is about. You were trying to develop a model that explains your observations. So, yeah, we can sneer at epicycles today, but let's be honest, they worked pretty well. Well, we began to eliminate them with a series of revolutions that happened in science. So the first one was Copernicus, who came up with a model of the universe. He noted that if you put the sun at the center, you made the Earth just another planet, along with all the other planets that orbited around the Earth. Those epicycles went away, and you got a much simpler model that explained the structure of our solar system. To make further progress, we needed to have data. And so a lot of this was sparked by, it was a time of great ferment in the 16th century. So one thing that really sparked a lot of this was a nova stella, a new star that appeared in the constellation Cassiopeia. Now, there shouldn't be anything new in the sky in the Ptolemaic frameworks. This was telling you, you know what, this dogma we've been carrying around for the past 1,000 years, maybe we should be rethinking that. Not everyone was too keen on this, but gradually it began to happen. Partly inspired by this, a rather eccentric Danish nobleman. If you haven't read anything about Tycho Brahe, I urge you to read at least a short biography of him. Very interesting fellow. I wouldn't want to spend too much time personally with him, I think. But he did important things, and we honor what he achieved. So one thing that he did was he built an observatory and spent a lot of his life just precisely cataloging, as a function of time, the positions of all these things in the sky. He didn't do that much with this, but his employee, his associate, Johannes Kepler, did study this, and he indeed discovered that all the motion of these things could be reduced to 3 simple laws. This entire complicated multi-decade data set could be explained by saying that he basically held this geocentric picture where the sun is at the center and the planets are going around it, but they don't move in circles. This bothered people, right? Because a circle is perfect. And so we're breaking a level of perfection here. So indeed, what Kepler found was that if you put the sun at the focus of an ellipse, the planets would then move around that ellipse. In this framework, you then find that as the planets move around this ellipse, they don't maintain the same speed. Imagine there's a long thread that connects the planet to the sun. Then over the course of, say, a month, the planet sweeps out a triangular area that looks like this. Later in the year, over the course of a month, the planet sweeps out an area that looks like this. These areas are equal to one another. And they showed that the motion is such that in equal units of time, you sweep out an equal amount of area. He also showed that these things are in ellipses, which are described by a geometry. They have a semi-major axis associated with them. Square the semi-major axis, and that tells you, square the orbital period, the amount of time it takes to go around an orbit, and that's going to be equal to, up to a constant, the cube of the semi-major axis. This was a beautiful sort of phenomenological thing. This came out of the data. There was no theory predicting it. It was just an explanation. You went through and it was a pattern that fit the data. Revolution number 2 came from Isaac Newton explaining that all 3 of these laws were due to a universal law of gravitation. He showed that all 3 of these things could be explained by stating that 2 objects are attracted by a force that is proportional to the product of their masses and inversely proportional to the squared distance between them. This ended up being something that it turns into a simple mathematical formula and explained all of these laws. As I was doing research for this talk, I realized that there was a possibility of an even earlier revolution that was overlooked. Although Brahmagupta is best known really for introducing 0 to mathematics, he introduced a notion of, I'm not going to attempt to pronounce the Sanskrit, but he introduced this idea that objects fall on the Earth due to a force of attraction by the Earth. Therefore, the Earth, the constellations, the moon, the sun, he got a few of the details right, but he had this idea that all these things that are moving around, it's the same basic force as what causes an object to fall near the surface of the Earth. So this idea of a universal law that could have been used here was actually written in India 1,000 years before Newton came along. A bit of an overlooked revolution. Would have been, it's fun to imagine an alternate history where there was better communication and this was more widely disseminated. At any rate, Newton certainly gets credit for providing this quantitative description of things. Okay, and the fact that it was universal and quantitative, you were able to precisely describe the rate of objects falling at the Earth's surface. You could describe the orbit of the moon around the Earth, the orbits of planets around the sun. Shortly before Newton's discoveries, or before Newton formulated these laws, the moons of Jupiter had been described. And this law worked for them as well. This is amazing. Every one of these phenomena was not just explained, but very accurately explained. And indeed, we still use this today. Okay, we're going to see there's some corrections to this, but they are small in most circumstances. This was appropriately celebrated, and I love to quote a little poem that was written by Alexander Pope in 1730. Nature and nature's laws lay hidden tonight. God said, let Newton be, and all was light. It did not last. The devil howling, ho, let Einstein be, restored the status quo. So what do we mean by this? From 1905 to 1915, Einstein reformulated all of physics according to principles of relativity. Okay, so this is, I teach several classes on this, so in the spirit of some of the talks that were happening in our morning session today, I'm going to try to teach you about general relativity in approximately 30 seconds. So much of the impact, what we care about, basically boils down to two simple rules. So the one equation that if I were giving this talk back home, I'm confident my mom would know, E equals mc squared. What this tells us is that mass and energy have an equivalence associated with one another. Now we know from Newton's laws of gravity that mass is attracted by gravity. This tells me that all forms of energy should in some sense, perhaps a bit of a subtle sense, but in some sense also be subject to gravity. Relativity also tells us that the speed of light, c, must be a universal limit. No information, no signal can travel faster than light. So let's look at the consequences of these. So the first one, light is energetic. Light must respond to gravity. A consequence of this is that if I have a little beam of light and it climbs out of a gravitational field, it gets redder. So you can all see here, I've got a green light from my laser pointer. And look at how much redder it is up there. Okay, now there's two ways in which I'm cheating. First, what you're actually seeing are the photons that bounced off and came back down. So all the red shifting that they got going up, turns out it gains energy and it gets bluer as it comes back down. So in fact, you see it just like this. So if someone wants to go and get maybe a 15-meter ladder and climb up there, if you were to go up there and study this, you should see that that spot of light is slightly redder than the spot of light down here. If you could actually measure that precisely, I would wonder what planet you are from, because the shift is so slight, there is no way human eyes can discern it, but very precise measurements can. And indeed, despite my joking about what a subtle effect this is, I would wager that every single person in this room has used it, possibly even today, because it is central to the way the global positioning system works. Okay? Most of us have a GPS receiver in our pockets. And they are in communication with satellites that are orbiting the Earth. As the radio signals between those satellites travel back and forth, they're comparing sort of time on the Earth to things that are happening in the sky there. We have to correct for this in order for them to work. If you do not, the GPS accuracy would degrade by 8 meters per minute. This is not a small effect. So in addition to the fact that light turns red as it climbs out of the gravitational field, it is bent, right? If I do a perfectly horizontal path here, in fact, if I could measure this very precisely, I would find that as it moves across the surface of the Earth, it's deflected downward a little bit by the Earth's gravity. This, it's a small effect on a human scale, so that we really need astronomical scales for it to build up and for us to see it. And indeed, this was first observed by looking at the apparent shifts of positions of stars during an eclipse of the sun. Okay, so the sun's gravity is able to bend light by a couple of arc seconds, enough that a good telescope can pick it out. So let's imagine gravity that is so strong that light bends and redshift completely away. To put this together, what I want you to do is imagine just a ball of gas, okay? And imagine that this ball of gas cannot support itself against its own gravity. And so with time, the ball is going to compress into smaller and smaller spheres. And as I do so, the gravity at its surface is going to get always stronger and stronger. The amount of mass remains the same, but the radius is getting smaller. And so remember, the gravitational force at its surface goes like its mass and divided by its radius squared. It'll get so strong that eventually we're going to reach a point where light is bend so sharply around it can't ever get away, and indeed, it will redshift so much that the beam of light would just never escape. We trap it entirely. The event horizon is defined as the surface that divides light rays that can get away from those that cannot. This is a concept that's going to come up repeatedly in this talk. In particular, this is going to come up because the dynamics of the behavior of the light rays that make up an event horizon are described by this beautiful equation that was derived by Professor Raychaudhuri. What we're interested in here is we can think of the technical term we use to describe such a sort of a bundle of light rays as a congruence. And what Raychaudhuri's equation tells us is how does such a congruence evolve as it moves through space-time? And it's governed by an equation here. So for those of you who are familiar with some of the technical details, this theta is telling me something about the rate at which it's expanding. This sigma is telling me about the rate at which light rays are sheared. So imagine they're perfectly parallel to one another. That's sort of saying that there's actually a little bit of a shift in that parallelism. These two terms are the particularly important ones. Omega is related to sort of the way it tends to rotate. That's going to turn out to be not so important for us. And this TAB tells me about the amount of matter and other things that are in the space-time. I'm going to ignore that for the purposes of simplifying a few things here. So one thing which I want to emphasize, and in some sense, I think this is even under-recognized by many people in the community. Raychaudhuri's equation has often been used to study the properties of singularities. You'll get the behavior of matter moving, the way that they move through space-time. But it applies to any bundle of rays, matter, light, anything that follows this kind of motion. What I'm going to talk about a little later in this talk is that one can show, using this equation, that an event horizon interacts with orbiting bodies. If I have a black hole and there's something near it that's moving around, that is going to change the properties of the event horizon. And the way that it changes will then actually back react onto the orbit, and it'll affect quantities that we can measure. Hold that thought. We're going to come back to that a little bit later. I also want to go on a brief digression here. So I earned my PhD, as this beautiful introduction said, in 1998, supervised by my academic father, Kip Thorne. Kip earned his PhD in 1965, supervised by my academic grandfather, John Wheeler. Professor Raychaudhuri earned his PhD in 1960, in part due to a beautiful external review that was provided by John Wheeler, who really highlighted what a game-changing, important piece of work this was. A lot of his work was a little underappreciated at that time by many people, and I think Wheeler's input made it really clear that this was one of the most important pieces of work in general relativity to be done. So if it's okay with everyone here, I consider him to be my academic uncle. All right, let's talk about astrophysical black holes. I've been describing things in relatively esoteric terms up till now, somewhat abstract terms. Let's make it less abstract. When we go back and we look at what the conditions that define a black hole, we're looking for an object that is massive but also very small. It's very dark. They are going to be very hard to find. And indeed, just as John Mitchell's comment said, much of the best evidence for them over the years has come from looking at the motion of luminous bodies that are near them, that are influenced by their gravity. So a beautiful example is when we look in the center of our Milky Way. So over decades, it was established that this region of the galactic center, so this is quite a large region here, it was very crowded and very dense. There were a lot of stars. There's a lot of gas and dust, but it was all packed into a relatively small volume. One of the things that drove the development of instrumentation in astrophysics and astronomy was to try to really resolve that inner region better and better. And as we looked, so this is data from the Chandra X-ray telescope, we looked in that inner region, we kept finding that there was a little hot spot in the center there, far hotter than could be explained by just a star or something like that. It was best explained by some kind of very compact gravitational source with a lot of matter falling onto it, getting hot, and generating X-rays. Then people were able to zoom in and look at the motion of stars in the center. There's a bright dot that's here just to guide the eye, but when you actually look at this thing, there's no bright dot there when you look at it in optical light. These stars are just all orbiting around some dark object. By looking at the properties of their the properties of their orbits, you can weigh that dark object, and it's 4 million times the mass of the sun. Over the years, people have proposed many explanations for this, but the only one that really stands up, the one that has stood the test of time, And it's really been confirmed now that the Event Horizon Telescope has zoomed in and looked at some of the properties of matter accreting onto this thing, is that it must be a black hole. Okay? People used to still come up with models for these things. They sort of, after a while, they stopped trying to publish them in reputable journals. They seem to just mail them to me directly. These days, I think even that is happening a little less and less. Let's talk about this other aspect of Einstein's gravity that I mentioned. No information can travel faster than light. So in Newton's theory of gravity, information is transmitted instantly. So if I have two stars that are separated by many light years, and one of them moves, the red star immediately knows about the yellow star's new position in Newton's theory of gravity. It contradicts the idea that information has a speed limit associated with it. In fact, when you study freshman electricity and magnetism, perhaps maybe not freshman, perhaps maybe a slightly more advanced version, you learn that this also applies to electrodynamics. If I have a point charge, you learn this, you do learn in freshman electricity and magnetism, you learn that it produces an electric field that radiates radially in a spherically symmetric manner out from that charge. Now, if you accelerate that charge, there's a slightly different set of field lines that get set up according to the motion of this thing in the frame that you are now looking at it. And what you see is that at large distances away from that charge, points out there don't yet know that the charge has moved. So those field lines are pointing at where it used to be. Down here in this inner region, the field lines are pointing at where the charge is correctly, according to the fact that it's begun moving. And there's a shell that connects these two different regions. That shell propagates outward at the speed of light. I've just illustrated the electric field lines here, but there's actually an accompanying magnetic field lines to go with it. And indeed, this thing goes out at the speed of light. This is radiation. This is how light is made. Everything we see comes fundamentally from charges that wiggle around like this. The same thing has to apply in gravity. Okay, so you are all gravitationally attracted to my fists right now, okay, which aren't moving. And if I start going like this, the gravitational attraction for my two fists is varying. And so you are all feeling a time-varying motion. Those in the front row feel it before those in the back row. So I'm bathing you with a form of radiation associated with gravity as I do that. The way in which this shows up, that sort of kink in the field that communicates gravity, it acts like a tide. So you end up with this thing where there is a force that basically stretches along one axis, squeezes along an orthogonal one. Really think of it as just like the way the moon raises tides on the Earth. So it's kind of obvious how to look for this, right? Conceptually, it's easy. You just need to look for oscillations, put some widely separated masses down, and then wait for a gravitational wave to come along and shake them. All you got to do is make a way to measure that. Now, suppose you're proposing this experiment and you're going to go to your funding officer and ask for money to build it. First thing you should do is do a calculation. How big is the wiggle? Okay, now I'm not going to go through the details in this talk, but it's an exercise that you do when you study general relativity. It's not a very difficult one once you have the basics there. The punchline is that you find that the amount of oscillation here is proportional to the separation of those masses. And for every kilometer of separation, it's roughly 1,000th the radius of an atomic nucleus. That's the point at which that funding officer sort of picks up the phone and says, "Security, could you?" Well, my dear friend Ray Weiss, when I was 1 year old, wrote a prophetic paper describing how one could possibly turn this ridiculously impossible seeming experiment into reality using laser interferometry. And in the interest of time and because of the focus of this talk, I won't go through the details of what is really in this. But one thing which was clear is that he concluded that if you're able to control noise really well, and dear God, is that important, as my colleagues who are in the LIGO science collaboration are very well aware, and with well-designed, very powerful lasers, this can be done. This was not possible in 1972, but it defined a program of research and development that drove the next several decades of Ray's career. And the basic idea here is to use the fact that laser, indeed all light, but lasers in particular that are in a very pure state, consist of a wave. Okay, so I shoot light through a beam splitter, bounce it down, send it down a set of arms and bounce it off a bunch of mirrors. What happens, let's look at it in its wave-like form. We set this up such that when there's basically nothing interesting going on, when the light recombines, the light waves destructively interfere with each other. so that my photodetector over here measures nothing. That's sort of the baseline situation. This is a bit of a cartoon. My apologies to my experimental colleagues. As these things move around, we break that destructive interference pattern, and that encodes the idea that something's come along and changed these positions. What Ray was able to show in this is that by making a measurement like this, you can actually measure a shift trillions, 10 to the minus 12, times the size of a laser wavelength. It's an amazingly precise measurement. This idea is what led to the construction of the Laser Interferometer Gravitational Wave Observatory, currently consisting of 2 sites, one in Hanford, Washington, one in Livingston, Louisiana, sensitive to gravitational waves in the human audio band, a point we're going to come back to. It's good to have 2 sites, helps you to protect against noise, and it gives you a lot more information about the waves. Soon to be joined, we hope, by a 3rd LIGO site here in India. Right now, we also have a detector in Italy built by a French-Italian partnership. Very similar, slightly smaller, but essentially does very similar kinds of operations. And current operations are also joined by a detector that's in Japan that is not nearly as far along yet in sensitivity. They're working on some very advanced techniques to try to reduce noise. But many of their scientists are participating in the LIGO data runs and are deeply involved in this collaboration. How do we make these gravitational waves? So remember, I want something that sort of is wiggling around. And I'm going to make the waves strongest if I have something that is very massive and moves very rapidly. So I'm going to want things that are very dense and very compact. The ideal source is going to be something that involves black holes, 2 black holes in particular, because I need to break the symmetry that a single black hole has. So although there were some back and forth with our astronomer colleagues over the years, it was clear to some of us, at least, that black holes were likely to be very strong sources as these detectors began operating. So black holes are entirely described by 2 numbers, their mass and their spin. So when I look at the gravitational waves that they produce, mass and spin should really be the most important things to determine what the waves, what kind of their properties are like. So I'm showing you here an example. So for the experts in the audience, this is a post-Newtonian waveform that's been calculated for 2 black holes. I forget exactly what the masses are, but they are non-spinning. What we see is that as they orbit each other, they lose energy due to the back reaction of gravitational wave. Gravitational waves carry energy away from the orbits, and it causes them to fall towards each other. As they fall towards each other, they start moving faster. That makes the wave stronger, and it makes the frequency higher. That makes the wave, because the wave's stronger, it now loses more energy, which makes the amplitude of the wave stronger and the frequency even higher. So you get this form where the amplitude is just continuing to grow and the frequency sweeps up. Those of us who have been sort of in theory in this field for a while, I was present when people first began to think about how we would go and measure these. And a very important moment was at one point, this was 1993, 1994. There was this new technology that people were developing called computational neural networks. And I remember Kip Thorne sent myself and another student to talk to a group that was developing these things called computational neural networks. They were very new at that time. We weren't sure if they were going to be any good, but we figured, sure, why not? And so we talked with this postdoc in the group about what we were doing. And the postdoc said, what's the frequency band of your signal again? We said, well, it kind of goes from about 10 hertz up to about 1,000 hertz. And he says, you know, that's human audio. We said, yeah. He says, the ear is a really sensitive spectral discrimination device, and it's already connected to a good neural network. And so we thought, this might be a really interesting thing to do, just to turn this into a sound and see what it tells us. So hopefully the sound is still working properly. I have encoded this so that we can hear what 2 coalescing black holes sounds like if the gravitational waves could be converted into audio waves. So you can hear it. The frequency gradually grows, the amplitude gradually grows. That is the sweep of this thing as it proceeds. Let's now make those black holes rapidly spin. Spin is the only other property that a black hole can have. And depending on how rapidly it is and what the geometry of it is, there's a lot of complicated stuff that can happen. But you can see already in this example, for a nice long waveform, you get all these additional wiggles here. What's going on is, remember, E equals mc squared. All sources of energy gravitate. A spinning body gravitates in a way that's different from a non-spinning body. And the interaction of that spin structure has a form that looks almost magnetic-like. And so what we find is that it's kind of like when you put a bar magnet in a magnetic field, it feels a torque that makes it want to twist. The spins of these black holes act kind of like magnets in a magnetic field. They're wanting to twist around. That causes them to precess. And that precession is what leads to these additional wiggles. You also know if you have two bar magnets and you change their orientation, the force between them can vary. That leads to, in the case of two black holes that are spinning, modifications the way they interact with each other gravitationally. Let's see what this one sounds like. That additional that kind of a structure, that is encoding something very fundamental about the nature of these objects that we're attempting to measure. One last example. So in general relativity, there's no intrinsic scale to it. Everything goes with the masses of these objects. Just as a very small bell will make a high-pitched tinkle, a very large bell will make a very low-pitched bong. If I have massive black holes, they will make much lower frequency gravitational waves than small ones. So if I do two black holes that are quite massive, what I'm going to get is it's a signal that looks exactly the same, but everything's been shifted to low frequencies. And if I ask what piece of that signal is in the band of the detectors that I'm trying to measure, you find that the only thing that is sort of audible to your detector are a couple of these last little cycles that are associated with the two black holes colliding with each other and then settling down into a single isolated black hole. Let's listen to what that is like. When you look at the mathematical form of these things, it's a damped sinusoid. It's exactly the structure of a bell that is losing its energy. Okay, and so we call this the ring down. And the detailed nature of this ring down is set by the properties of the black hole. Depending on how massive it is, how rapidly it spins, that determines everything in this signal. And indeed, one thing you might notice though, it's not much of a bell, right? We call it a ring down. That's a pretty lousy bell. What's going on is that it actually loses all of the sort of cycles. They radiate away very, very quickly. And that can be understood in terms of sort of an interesting property of the event horizon that's going to come out when I connect this again to the work of Professor Raychaudhuri in a couple of minutes. But I do like to leave you at this point with an aphorism from an old colleague of mine. Black holes don't ring, they thud, okay? That just refers to the fact that this thing decays away so quickly. All right, so if you were here this morning, you all heard some bits of this. So when one of the most interesting days in the life of many of us was actually officially the day before LIGO was supposed to begin its operations with advanced sensitivity. But there's a saying in English, if it ain't broke, don't fix it. So everything was sort of working reasonably well. So we were like, just don't touch it. Okay, let's just let it go and see what happens. And thank goodness they did that, because for most of the time, you just saw the data from the two interferometers. It looked just like noise. And then suddenly, bam, something came along that kind of changed the lives of many of us. Notice that sound is not that different from that little thud that I played for you a little while earlier. One difference is you hear noise, right? The first one I played for you, that's what comes from a theorist. This is what somebody actually measured. So it became clear when we did detailed analysis of this that there were a 29 solar mass black hole had merged with a 36 solar mass black hole and left behind a 62 solar mass black hole. I'm trying not to put too much math into this talk, but I will point out that 29 plus 36 does not equal 62. In 0.2 seconds, 3 solar masses vanished. If this had been light, this would have shined as brightly as 175 billion Milky Way galaxies for those 0.2 seconds. Instead, a couple test masses shook by a little, a fraction of the size of an atomic nucleus. That is a statement of the fact that gravity is fundamentally a weak force, a lot of energy bound up in a small effect. This was rightly celebrated. So we see Ray, who conceived this thing a long time ago and played a major role in marshalling it along, putting together the collaboration. These three gentlemen were celebrated for this. My PhD supervisor, Kip, who played a major role in thinking about what goes into measuring it, thinking about the sources that go into this. Barry Barish here in the middle, who rescued the project at a time when it really needed help and did a tremendous role in making the experiment come to fruition. But I want to emphasize that these three were kind of the public face, and indeed, every one of them will say that they accepted this award really on behalf of the thousands of people around the world who contributed to this project. And although this is a talk in honor of Professor Raychaudhuri, I have to take a moment to honor Ray Weiss, who we just lost a couple months ago. Sorry, he was a dear friend of mine. He contributed a tremendous amount to science, not just gravitational wave observatories, but he played a fundamental role in developing atomic clocks. He made tremendous contributions to developing measurements of the cosmic microwave background. And he was a mentor, he's an advisor, he was a friend to many, many scientists. Every time I saw him over the past couple of years, he was getting a little frail with time, but he would still come onto campus. He would always have hard questions when people were talking about science, but he would always pull me aside to say, how's your daughter doing? How's school these days? He always wanted to know about our families and how people, the humanity of them. So, you know, he lived a good, long life, but we miss him. The most recent catalog of these events, we now have over 200 events, and indeed, when these detectors are operating properly, and you know, these are sensitive things, so having all of them on at once is relatively rare. One of the benefits of putting additional detectors in the network, as has been emphasized by some of the talks this morning. We measure a couple of these things a week, okay? So, you know, for me, this is mind-blowing. When I was a graduate student and I was talking about the importance of binary black holes, a lot of my astronomer friends were kind of like, so what you want to do is study unicorns. Okay. But indeed, it turns out there are herds of unicorns, and they play an important role in these things. This plot has been shown several times. What I kind of want to emphasize here is that in this plot, the red dots represent, so the vertical axis is mass. The horizontal axis doesn't really mean much. I think it's just arranging all these points so that the pattern looks cool. All the red dots tell us about the discoveries and the characterization of black holes that have been found using X-ray telescopes, optical telescopes, radio telescopes, the electromagnetic interaction. All the blue dots are the black holes we've characterized using gravitational waves. I remember giving a version of this talk about probably sometime in late 2016. Where I had a version of this plot that had pretty much all of these red dots and I think 3 blue dots on it. And I kind of went, I can't wait until we have almost as many as the red ones here. And it's stunning to me how quickly this has expanded. Okay, this has really turned into a black hole discovery engine. I want to highlight one particularly interesting event that was just announced a couple of months ago. It looks remarkably similar in its characteristics and its waveform to the gravitational wave that was first detected. But in the meantime, people have not been resting. The detectors have gotten better. And so our precision with which the various masses have been characterized is much better. And when you zoom in and you really look at the structure of that late waveform, that ringing structure at the end has been characterized far more precisely. And indeed, in order for this to really describe the data, it requires an exquisite match to a model of a system that has an event horizon, one of these surfaces of light rays, that are going to play a big role in what I talk about in the next couple of minutes. So let's move to the future. So LIGO is going to continue operating. CAGRA will be getting better. Virgo is going to continue operating. GEO, and I think TAMA may have been decommissioned. That was a Japanese prototype instrument. GEO is still around. It's a small-scale detector in Germany that's largely used as a testbed for developing advanced experimental techniques. Our friends in Australia were hoping to join the network, but their funding agencies decided, they had to make some strategic choices, so they dropped out, and I am so happy that LIGO managed to develop a partnership with India so that we are bringing India into this as well. And 2030 is the timeline to get things going. So construction tenders were apparently issued a week ago today, or at least there were bids for them a week ago today, yeah. Bids were issued, and so the process is underway. I have to show this thing here. One thing which is very important, so 2 things I want to emphasize in this. So first of all, you can see many of my friends here meeting your prime minister for the original signing ceremony. My friend Rana apparently overslept and forgot to put some good clothes on before he met the prime minister. But nonetheless, he's in there, and we had this beautiful ceremony shortly after the discovery announcement. What I really want to emphasize is that even as there's plans to develop very large-scale detectors in North America and in Europe, even if they make things that are much more sensitive, having a detector in India will be tremendously important for gravitational wave astronomy. It gives us this incredible ability to pin down events on the sky and for us to follow them up with other telescopes to learn things about them. I'm going to spend a little bit towards the remainder of my talk talking about a detector that is being developed to fly in space. So the laser interferometer space antenna, it's going to consist, let me restart this animation, 3 spacecraft that are independently orbiting the sun in an orbit that trails the Earth. And they do so in such a way that even though each one is individually moving on its own orbit, the pattern that they hold looks like an equilateral triangle that slowly rotates as it moves through, through its orbit. This whole lot that can be said about this, but I kind of want to emphasize is that this will listen to signals at frequencies that are about 10,000 times lower than detectors on the Earth. And remember, as objects get more massive, the frequencies move down. So by making the frequency band so much lower, you've opened up your sensitivity to objects that are millions of times the mass of the sun, not dozens of times. In particular, this opens the window onto processes that involve the massive black holes that astronomers have found that reside in the core of many, many galaxies. So there's a lot that we could say about that, but I want to move on to a few other things. I want to give you one example here of the kind of thing that we want to see. So what I'm going to show you is an example of a particularly interesting source that consists of sort of a stellar mass black hole orbiting a million solar mass black hole. So let me set up what we're going to hear for a second. This object is, binaries like this are expected to form through kind of scattering events. So when it's in a dense star cluster, there's a lot of interactions. Professor Chatterjee gave us a talk this morning talking about the way that events like this can form binaries that LIGO is listening to. But they're also expected to produce things where occasionally a sort of 10, 20, 30, maybe 100 solar mass black hole is put onto a strong field orbit of the big black hole in the center of a galaxy. That orbit will be very elliptical. It'll be sort of stretched out like a comet, and it should have no particular orientation, right? So it should be kind of randomly oriented. So it's going to have a much more complicated gravitational waveform than the ones that we've been measuring to date. Because of the mass ratio of the system, it will also last much longer. Now, indeed, part of the reason it lasts longer is that the masses are all higher. So for us, one of the important things about the slow evolution is that these things will last for probably tens, maybe even hundreds of thousands of orbits. So one of the things that my colleagues and I are trying to do is to develop models that allow us to track those tens of thousands of orbits and use that as a way of precisely measuring the properties of that black hole and of this binary. Now, what you're going to find when it's on an elliptical orbit like this, remember, go back to Kepler's law. Okay? The thing moves fast when it's near periapsis, and it moves slow when it's near apoapsis, when it's far away. When it moves fast, you have a loud gravitational wave. When it moves slow, you get a quiet gravitational wave. This leads to this thing having a buzz. That buzz is the contrast between the loud moment when it's close to the black hole and the quiet moment when it's farther away. As the in-spiral proceeds, you can hear all the frequencies moving higher and higher. That's because the orbit is gradually getting smaller. There's also a bit of a flattening of that buzz. That's because it's becoming more circular. The contrast between the two modes of motion are less. My apologies for your ears. This version of this video, a student of mine made it many years ago. In fact, this is actually based on an approximation of things that we can compute a lot more precisely now. We're due for an overhaul. But this video, the original version, it was so old that if it reached the last frame, it used to reboot my laptop. And so I actually put in a stop. So it doesn't do that anymore. I should correct this, but that's why what we would see, and in fact, the talk I gave at the Saha Institute yesterday, I did do this, is that this thing plunges into a black hole and it just goes away. You just have a quiet system after that. Now I want to tell you a little bit about some of the physics that went into that calculation. The radiation that is generated by these orbits back reacts on the system, okay? And so the radiation has two components to it. First, there's energy that is carried off to infinity. Okay, radiation goes out, it flies away from the system. This is just like electromagnetic radiation when I make my charges vibrate. So I'm going to shoot a laser beam at the wall. That laser beam is coming from my battery in this case. But if I do this long enough, I will take all the energy out of the battery. There's another contribution, though, which is that some of this radiation goes into the black hole's event horizon. Okay, black holes, that the stereotype is that everything gets sucked into them. It's not quite correct. They're just a surface of no return. Things fall into them. And what's interesting is that these two contributions have somewhat different behaviors. The flux to infinity always takes energy away from the binary, just as you would expect. The energy going into the event horizon, it takes energy away from the orbit if the orbit moves faster than the black hole spins. So what I mean by that is imagine the black hole is spinning like this, and the orbit is going around it much faster. Okay? So if that's the case, when I have this separation between those frequencies, the radiation down the event horizon takes energy out of the orbit. On the other hand, if the orbit is actually slower than the black hole spin, the orbit gains energy from this contribution to the event horizon. That's weird. Nothing is supposed to come out of a black hole. And yet, in the mathematics of our calculation, we find that a quantity that is formally defined by, for the mathematicians in the audience, an ingoing boundary condition on the event horizon takes energy out of the black hole and puts it into the orbit. What's actually going on is that you're transferring some of the spin energy into the orbit. I want to emphasize that this is actually not a small effect. So there's a lot of details here in this thing, so I'm just going to summarize what this is telling us. So on the left, what I've done is a bunch of calculations where I've calculated how a body evolved through orbital parameter space, doing it in the pure general relativity calculation. I have energy going to infinity, I have energy going into the event horizon. And especially for shallow inclination, it takes about 1.5 years for this in-spiral to happen at these mass ratios. Now suppose that I find on top of some big tall mountain, sort of a secret tent, guarded by monks perhaps or something like that. And inside there's a dial that says event horizon boundary condition. I take that and I change it from 1 to 0. In doing so, I turn off the energy that goes into the black hole's event horizon. I find that the in-spiral happens faster by weeks, up to 4 weeks, almost 4 weeks faster. That is a huge effect, and it changes the number of orbits that I'm tracking with these measurements by tens of thousands. My colleague Shayak Datta is now a postdoctoral scholar in Italy. I've been collaborating with him on how well we can measure these things and use it to learn about these systems. And what he has shown is that I sort of made this joke that I found this tent, at the top of a mountain where there's a dial that goes between 0 and 1. The question Shayak and I and our colleagues asked was, how much do we have to change that in order that we can actually discern it from the statistics of just noise? And we can actually tell the difference between the general relativity value, call it 1, and 0.9999. We can make a very precise probe of the nature of the event horizon. But what fundamentally is going on? And I think the best way to understand this is by virtue of the fact that exactly the same behavior is seen in many other astronomical systems. Consider a moon that is orbiting a planet, okay? So the moon's gravity raises the bulge on the planet. That's its tide. Now, the planet is spinning on its axis, and the moon is moving in an orbit. If the moon is orbiting faster than the planet spins, what happens is the moon gets ahead of that bulge, and the bulge exerts a torque that pulls back on the orbit, and it takes energy out of the orbit. Energy moves from the orbit into the planet's spin in that case. If you're in the other limit, where the moon is orbiting slower, the planet is spinning faster, the planet's spin drags that bulge ahead, and it exerts a torque that tends to move energy from the spin into the moon's orbit. This is, in fact, exactly what we see in the Earth-Moon system. Our day is getting longer at a rate of, I forget exactly what it is, but on the order of milliseconds per year or something like that. And the moon's orbit is gradually increasing in radius because the energy associated with our spin is moving into the moon's orbit. This is exactly what we see in these black hole systems. So given that this pattern is exactly what we see, is this just a cute analogy, or is there something to this? So the answer is there absolutely is something to this. And the answer to this is in the Raychaudhuri equation. So at the core of this equation, what I'm going to do is apply it to a black hole's event horizon. On that event horizon, I can get rid of the rotation. I'm going to ignore matter fields, and it's simply given by a somewhat simpler version of this. The early 1970s, Stephen Hawking and James Hartle used a version of this equation. They reformulated it to show that if some kind of an external stress, say due to a tide of an orbiting body, perturbs the light rays that generate an event horizon, then the horizon's area grows. Remember, this theta, this parameter theta, tells me about the expansion of these light rays. And so I can quickly turn that into an area. Now I have to change coordinates a little bit, and when I do that, I pick up a factor here that's known as the surface gravity of the black hole. You can kind of think of this as telling you something about, if you were hovering right outside the black hole, how strong of a jetpack you would need in order not to die. So if I take this relationship, and now I insert some famous results from Stephen Hawking and Jacob Bekenstein, this temperature of the black hole the surface gravity is directly related to the temperature that Bekenstein and Hawking ascribed to a black hole. The area is directly related to the entropy of that black hole. I can turn this into an equation that looks exactly like a relationship that tells me about how entropy is generated in a flowing fluid. So Raychaudhuri's equation tells me that an event horizon looks just like a two-dimensional fluid, and it tells me it has a viscosity. If I gather together a group of constants that emerge in this thing, I wind up with something that has exactly the right units here. And this actually turns out to be a very large viscosity. So if I disturb this event horizon, this pattern tells me that it's kind of like a soap bubble, but it's a soap bubble that very quickly damps down. That's why black holes thud rather than ring. So using this, student and I thought this was pretty cool, and we thought this would be sort of a good way to visualize how it is, this down horizon radiation. We want to see how it's connected to this sort of tidal bulge picture and see whether, there's this picture of a bulge that's raised on a planet and how it interacts with a moon. So my student Stephen O'Sullivan and I started to make movies showing what would happen if I have a little body come in and interact with the black hole. And indeed, you can see there's a tidal bulge. It tends to be misaligned with this thing, and the pattern with which it draws there, it perfectly syncs up with what it needs to do to explain these kinds of behaviors. So I'm going to conclude here. It's a lot more that we could say, but I really want to end this on sort of this celebratory note of the man who we are honoring. So we have now entered, as many of the talks this morning told us about, we're in a completely new world of astronomical discovery. It's going to get even broader, and there's going to be more details, more precision, as we expand our ability to probe the dense and dark universe using gravitational waves. So I'll just conclude by saying thank you to Professor Raychaudhuri. Thank you.
Yeah, question.
Let's wait for the mics. I'm going to get some water.
Hi, Scott. Very nice talk.
Thank you.
So when you were giving this analogy of the moon, that it's moving slower, and finally, let's say the black hole speed is larger than the orbital speed of the, or what should I say, the rotation speed of the smaller black hole.
Yeah.
So would it eventually go out and not?
So that's a question. So one thing that's a little bit different with two black holes versus the Earth-Moon system is that, so like in the Earth-Moon system, we have actually a relatively strong coupling of the sort of tide to the orbit. We have no measurable loss of energy to the gravitational waves going out to infinity. Okay, and so because of that, that's the only thing here. Now, when we're talking about a black hole system, the flux all the back reaction that's related to things going off to infinity is always much more important. However, if you go back to when people first started thinking about things like this, and so this notion that the sort of flux down the horizon can kind of have the wrong sign and do things, that got people really excited when black hole perturbation theory was first beginning to be explored. And you will see papers that describe searches for what are called floating orbits. A floating orbit would be one where you sort of somewhere, there's a perfect balance between that and the flux out to infinity. Now, you can look for this. I mean, the effect is strongest if the black hole is spinning very, very rapidly and the orbit is circular in a strong field. And you can use that and try to find these floating orbits. They don't exist in 3+1 dimensions, at least. There's some speculation that in other crazy theories and additional dimensions that the situation may be a little bit different. But you know, the sort of fact that it does slow it down, it's showing you there's kind of this trend in this direction. But the radiation to infinity always wins.
Very nice job.
Thank you.
I had a comment rather than a question. This is about this last part where you try to relate the Raychaudhuri equation, the horizon, as a membrane in which there is a fluid with viscosity. If you look at the original derivation of Raychaudhuri equation, amazingly, fluid mechanics is an inspiration. It uses.
I know. Isn't it beautiful how it all comes together? It's very much all full cycle. One of the things that's a little bit subtle is that to go from, forget it, I'm having trouble. Zoom and my keynote are not playing well together. So let me just say this in words. When you go from the standard form of the Raychaudhuri equation to the Bekenstein and Hawking form that derives the rate of growth of the area, there's this term involving the surface gravity, which comes from essentially changing the parameterization to one that is appropriate to someone who's observing sort of far away. That's the one subtlety that I think takes a little bit of care to get in there correctly. But that aside, you know, this inspiration was absolutely, it's beautiful that it's come full circle. Yeah.
The gravitational detectors for Earth.
Sorry, can you say it again, please?
The detectors for Earth, the land-based gravitational wave detectors, which have at least 3 detectors to rule out the noise with a real gravitational wave. But what about LISA, which is in space, which don't have at least even 2 gravitational wave detectors, and the Earth isn't even shielding the detector from other noises.
Yep.
Where the noises are the gravitational waves from other sources itself.
Right.
So while there, how will we detect that it is a gravitational wave but not a noise, and the noise is from this source, not that source?
Right. That is, I'm going to give you the short answer. The even shorter answer is that working out how to answer your question is the center of the careers of several hundred people who are now designing this mission. Okay, what you're saying is it's going to be hard. Now, one complicated as LIGO is, if something's not working right, in principle, you can go in there and fix it, right? This actually is in an orbit that trails the Earth by 20 million kilometers. Once it's gone, it's just bye-bye. You know, you're not touching it anymore. So one thing is that many of the sources are expected to be so loud that they actually will stand up above the noise without as much sophisticated data analysis. There's many other kinds of sophisticated data analyses to be done, but it's not hidden under the noise in the same way that LIGO and Virgo Kagra sources are. Also, the metrology, the way the measurement is done is actually quite different. So you don't have an L, you have a triangle. And what that triangle does is there are actually 6 different data lengths because there's sort of information going from this spacecraft to this spacecraft, from this spacecraft to this spacecraft. So there's 6 pairs like that. And so there are ways of synthesizing all those pairs of information such that they can be regarded as actually 2 independent L-type interferometers. So that's one of the things that is done to do some sanity checks. And there's actually a combination of those data trains that can be shown is completely insensitive to gravitational waves. It is only sensitive to noise. That is one of the ways you can actually help to calibrate that. Now, having said all that, No space agency would approve this, would launch this, would actually develop this thing without showing that the technology works in some sense. And so, somewhat overshadowed, rightfully so, by the LIGO discovery was that almost a month later, a test mission was flown that actually validated that the sort of measurement subsystem that operates in each spacecraft, whether it would work or not, they had a particular spec of noise that they needed to make, and they actually beat it by a factor of 10. So that at least shows that they appear to be able to isolate the vibrations, control the noise measurement within each spacecraft in order to actually do this. Unfortunately, we need, you can't make a 2.5 million kilometer lab on Earth. You can synthesize one by having light bounce back and forth many, many times. And people have done that to try to do some experimental tests of the measurement products. But this is a good example of some of the risk that is implicit in a mission like this. Another issue, which I'll conclude with this last complication. These sources, so the entire LISA mission is expected to be about 4 or 5 years. Each of these events lasts several months to several years. There could be dozens or hundreds of them. There are many other classes of sources that I've not talked about that also last for months or years at a time. So that means there's all these sources are on at the same time. And so you need to develop a data analysis algorithm that can detangle them all from one another. One thing that helps is that as the spacecraft moves in its orbit, it's got an antenna pattern associated with the measurement of a quadrupole field of gravitational waves, which varies with time. And the modulations associated with that variation depend on sky position. That helps to detangle different sources from one another. So that is my roughly 3-minute synopsis of what literally several hundred people are devoting their careers to doing.
Thank you for such a mesmerizing talk.
Thank you.
And, so my question was related to polarization of gravitational waves. So what I wanted to ask was, how is the polarization related to the shear term of the Raychaudhuri equation?
So that's a great question. So gravitational waves come in 2 polarizations. So this was shown in some of the talks this morning. So if you have one polarization, it kind of squelches and squeezes along axes like this, and you rotate by 45 degrees, and you can do the same thing. Mathematically, it comes about from a certain decomposition of a trace-free tensor. So you can take that shear tensor, which describes the tide acting on an event horizon, and you can break it down into 2 shear polarizations that correspond exactly to the 2 polarizations of gravitational waves. And in fact, when you go through some of the papers so when we talk about the polarization of gravitational waves, we talk about H+. That's one that in a particular basis measures gravitational waves along these axes, and H cross, which measures these axes. When you read the papers that we use to develop these things, we actually describe shear that is sigma plus and sigma cross, because the analogy is exact.
Thank you very much for the talk, Professor Hughes.
Thank you.
I actually have a friend who's been watching the live stream, so he has a question for you. Right. So his question
We are in the 21st century, friends. Okay.
So his question is that from gravitational signals, we can understand the redshift.
Yeah.
But we do not have any optical data for the black holes.
Right.
Right. So his question is, how are we understanding the mass of the primary black holes just from the frequency data?
So from the frequency data alone, you actually get a combination of the masses with the cosmological redshift. Okay, so and it's actually simple to understand this. So if you have an object that is expanding with the universe, imagine that object is a clock, right? So as it moves through the universe, we see that clock running somewhat slower if it's at if it's at redshift z equals 1, it runs slower than clocks here local to the Earth. If it's at z equals 2, it runs slower than that. The way that we infer masses fundamentally comes from the fact that the mass determines all the timescales of the orbit. Okay? So the orbit at a particular instant depends upon the mass and the separation. The rate at which it moves through a bunch of different orbits through different radii and changes that frequency, that depends upon the masses. So what we actually measure directly are time scales. And then we use general relativity to convert those time scales into mass scales. So if the source is at redshift z equals 1, we will see it moving at it will be, all those time scales effectively constitute a clock. And so that clock runs slower than it would if it was in our solar system. So what we directly measure is essentially mass in combination with cosmological redshift. However, we also determine the distance to the source. Assuming you trust your friends in cosmology, we can take distance and convert that into a redshift. And so by combining the measured distance with this redshifted mass, we can infer what the mass is. Now, even better would be if we actually had optical, X-ray, radio, whatever, an electromagnetic channel that allowed us to measure the redshift directly. Because what that would allow us to do is not have to rely on other cosmological measurements. It would be sort of self-calibrating. So far, we've been able to do that once with the binary neutron star event, which I have not talked about, but was discussed in some of the talks earlier here today.
So, first of all, that was a fantastic talk.
Thank you.
Now, I have a very basic naive question. Talking about the primordial gravitational waves, they will be much smaller in case as compared to the normal gravitational waves that we have detected.
Yeah.
So, talking about them, what type of noises are you expecting in that, and how are you expecting to get rid of that if we are able to detect them someday? Like I'm talking about the data from before CMB era.
Yeah, so the question here, so if we think about various cosmological processes are expected to produce a background of what are called stochastic gravitational waves, which are effectively random. You can think of it as a superposition of, trillions, just gajillions of like independent little oscillations on top of one another. And part of what makes it challenging, there's two things that make this challenging. One is that in all models that are kind of plausible, that are acceptable with respect to other things we measure on the large scale structure of the universe, these waves are very low amplitude. And so designing a detector that can actually find them is very, very challenging. Okay, it's a very much a worthwhile challenge, but to be perfectly frank, I'm not optimistic that we're going to see this sort of in the lifetime of my career, at least, because I think we do have to shoot really far. The other thing that makes it challenging is that they have exactly the same form as noise. And so distinguishing this sort of that kind of hum from this cosmological stochastic background from because you have noise in your instrument, which is which, right? One of the ways that you can do this, it actually relates to a part of the answer I gave to a question a little bit earlier. You can, with some instruments at least, you can formulate combinations of gravitational wave observables that are actually insensitive to the gravitational waves. So imagine you had an instrument that had a particular, at a very quiet level in a particular frequency band. You were measuring this sort of, white noise-like hiss, and then you compared it to a data channel that was insensitive to gravitational waves. And suppose when you did that, the noise level fell by a factor of 2. That would tell you that half of your signal in the other channel was probably a background of gravitational waves. You would want to go in and check that, obviously, but that might be one of the ways that you could distinguish between the two of them. This also, however, points to what one of the challenges is, which is that it's a comment that I sort of made in the talk I gave yesterday. There's a saying that medical doctors learn in the United States, which is that when you hear hooves, think horses, don't think zebras, don't think unicorns, right? And so if you have this sort of hiss, this white noise kind of a thing, you'd love it to be some exotic process from the early universe. Could also be a background of sources much more local to you that you overlooked, right? Could be merging white dwarf stars in our galaxy, for example, which are expected to contribute exactly that form of a signal. Could be things that are a little bit farther away, which are contributing sort of like that, but at a much lower noise level. That is, I think, one of the biggest challenges, is sort of finding a window to look for that kind of a signal that is free of a foreground of something that's a little more, a little less speculative and unusual.
That's it.
Hi.
First of all, thank you for a nice talk. So my question is, suppose there are random black holes in the late universe, and
In the what universe?
the late universe,
Late universe.
and there are also astrophysical black holes from star clubs. And so my question is, how can we distinguish between them using general observations?
It's hard. You may not be able to, right? So this is identifying what the origin of black holes is. So general relativity has a famous result known as the no-hair theorem, okay, which tells me that when I have an astrophysical black hole, it's characterized by its mass, by its spin, its electric charge, which astrophysically is expected to be zero because they will tend to neutralize very quickly. So effectively, just mass and spin, and that's it. I don't know how old it is. I don't know how it originated necessarily. I don't know what its progenitor was, right? Maybe it was a massive star. Maybe it was some kind of gas that through some weird process didn't form a star but just immediately collapsed. Maybe it's an alien civilization just got tired of having all their garbage pile up and they compressed it and launched it into space. Those, you cannot distinguish them from these observations. So this makes things really, really challenging. And so some of the best things we do, Professor Raychaudhuri gave a talk today talking about ways in which there are different formation channels that can make these sorts of things. Sort of from things that happen from various astrophysical processes, there's hope that especially as we measure longer wave trains and we get more cycles, stronger signals, we can distinguish, for instance, black holes that started out as two stars orbiting each other. Those two stars formed black holes, which then became a source for these events. If that happens, we sort of expect their orbits to be extremely close to circular. If they have spins, which they surely will, they'll probably be pretty much parallel to each other. Maybe they form through dynamical interactions in a dense star cluster, in which case their spins could be completely misaligned with each other because neither one sort of cares about the other when they encounter one another. If they form, they could have a lot of initial eccentricity, and perhaps they will merge with some of that eccentricity still there. So that kind of a thing we know how to detangle. At least we're figuring out how to detangle. But what you're asking is it's a hard question. This is, people write PhD theses on this question.
Yeah.
Yes.
Hi. Yeah, hi, sorry.
Yeah, so it was a mesmerizing talk.
Thank you.
I would again like to come back to this analogy between this Earth-Moon system, system of two compact objects.
Yes.
So we know that in the Earth-Moon system, the angular momentum is conserved. But
right.
In the case of two compact objects, because of the gravitational
That's right.
dynamic system evolves differently, then that means that rotational angular momentum plus orbital angular momentum is going to be conserved.
Right.
Does that mean that gravitational radiation can also have angular momentum?
Absolutely. Absolutely. Yeah. So indeed, when I generate these things, I have my governing equation. There's three integrals of the motion that I require that they sort of be conserved in a certain sense. So I require that the energy of the orbit plus the energy absorbed by the horizon plus the energy that goes off to infinity all sums to zero, or rather there's at least a balance between them. I do the same thing for all the components of angular momentum as well. It's absolutely a part of this, and it's indeed part of the formalism by which we do these calculations. Yes.
The calculation is explicitly.
Absolutely. It's used. It is built into how we do the analysis.
Just on this question, I'd like to this is the question that Amal asked.
Yeah.
Actually, from this university, this department, we wrote a paper on the angular momentum of gravitational waves, and Professor Ratna Pule and two other colleagues who are now in the US as graduate students. There's a paper which is being published.
Absolutely. I'm delighted to hear it. I mean, it's just as you can have angular momentum in electromagnetic waves as well. You just have to have the right multipolar structure, essentially.
Thank you, sir, for your fantastic talk.
Thank you.
So my question is that there is a supermassive black hole at the center of our galaxy. So how did it become so big? Really, how did it found like 4 billion times solar mass? how did it become so big?
That, again, is one of the most actively debated questions in astrophysics. Not just the one in the center of our galaxy, but the ones in the center of all sorts of galaxies. So when I'll give you some ideas, but let me just preface them by saying that every 10 years, the National Academy of Science of the United States commissions this study that sort of looks at what the big questions are. And for the last 3 times running, one of the big questions that drives the sort of program to develop new instrumentation is, how did the supermassive black holes get so big? What drives their growth? And part of the mystery is we don't even know necessarily how they formed. Okay, that's another open question. What did they look like? We believe that our universe is basically, it's about 13.8 billion years since the Big Bang. The biggest stars started to form probably a couple 100 million years after that. Did they form the first black holes? Were those black holes a couple 100 solar masses? And then did they grow into these really big things by accreting the neutral gas that was largely present there, merging with other black holes? Where is it possible for there to be sort of semi-stable supermassive gas clouds that then underwent some kind of instability and collapsed and formed 100,000 solar mass black holes, which then grew by accreting gas and putting all these things together? We don't know, right? And so this is, again, what you're asking is a fundamental question in astrophysics today. And people spend their careers exploring answers to this question. So sorry that I can't give you a good answer, but this is the kind of thing that drives what people think about.
Hello, sir.
Hello.
It's an incredibly inspiring talk.
Thank you.
So my question is that we are putting so much effort in studying gravitational waves and black holes, but after we overcome these current challenges, what are the informations or benefits we are expecting from them?
So I'm going to answer that on several axes. When I was a graduate student, one of the things I thought that these were going to be really important to do was, we sort of know in a very fundamental way, general relativity is an incomplete theory of gravity. It's inconsistent with quantum mechanics. There are mysteries like dark matter and dark energy, which could be different sources of gravity. They could be something fundamental in the field. And so I was really hopeful that with our measurements, we would start to see some deviation from the predictions of general relativity, which would guide us towards a deeper understanding of gravity. As we make our measurements more precise, I'm still sort of exploring this, but I will not deny that has become lower on my priority totem pole, because every single time we have done tests like that, general relativity has held up. And so, I think it is very likely that we've sort of, for at least foreseeable future, it's worthwhile for us to just say, let's give Einstein this one. Seems to work really well. Now what do we do with it? After all, you don't go around testing Maxwell's equations anymore. You use Maxwell's equations. So let's use Einstein's equations the same way. And so it's turning into, I would say, a tool for doing astronomy. It's a tool for learning about these objects, for using them as ways of understanding the way stars evolve and form and they leave behind. As we go to different frequency bands, we'll use these as a tool for observing the assembly of galaxies, using massive black hole mergers to trace the assembly of galaxies through mergers and things like that. Using it as a tool to map the expansion of the universe, study the evolution of heavy elements. So there's a lot of astrophysics and sort of fundamental kind of physics that kind of goes in there. But I would say another thing, which is not directly related to these science measurables, is that this is a tool of international collaboration. This brings together people who are curious about things, puts them in a room with people you might not meet otherwise, and really cuts across borders. And I think it's just been it's a hugely, I think in Professor Mitra's talk this morning, he showed all the nations that participated in the initial LIGO discovery, and it covers much of the globe. It's a beautiful thing. And so I think as a tool of international collaboration, not just gravitational waves, but a lot of science, I think that is, and anyone from my government is listening, pay attention, man, because we all get along really well and we learn things together and we make the world a better place. Well, so the question of, can we learn how it is that black holes got their mass? Indeed, that's an example of the kind of thing where as we're able to make precise measurements of their masses at different especially with the space-based detectors further back in cosmic time, we hope we will be able to get at least, I'm not going to claim we're going to answer it, but I think we're going to get information about it that'll guide people to think about how to answer it.
Thank you, sir, for the wonderful talk. And I have just one question that if when we are talking about gravitational waves, we are always talking about neutron stars and black holes.
Yeah.
So, is it due to the limit with what precision we can measure the gravitational waves?
It's a combination of that, because I've emphasized that you can think of gravitational waves as being kind of sound-like. Okay, and so the first things you measure and the things you tend to measure best are the loudest things, right? So if I was talking like this, you wouldn't hear very much. But if I start talking like this, now you've got everything, right? So the first source that we measure is going to be the loudest things. And so to get loud gravitational waves, you have to have a lot of mass moving very fast. In order for it to move fast, it has to be compressed into a really small region. So you need very massive compact objects. That picks out black holes and neutron stars as definitely the strongest. Other binary star systems should be doing it as well, though, right? And so, in particular, with the Laser Interferometer Space Antenna, the space-based detector, one of the most important expected, in fact, more than expected, we actually have, I can tell you why I think that this is the case. One of the biggest contributors to their data is going to be white dwarf binaries in our galaxy. Okay? They're not as compact, they're not as massive. There's a lot of them, and many of them are actually quite close to one another, and they move quite fast. We actually observe on the order of a half a dozen systems like this right now, whose, we can see these two white dwarf stars orbiting each other, and they sort of, it's two stars, each about half the mass of the sun, and they orbit each other with a period of about 5 to 10 minutes. Over time, we've seen the orbits get smaller. They're actually moving towards one another at exactly the rate that you expect for gravitational wave emission. So these, black holes and neutron stars are the main ones because they're the loudest, but they're not the only ones. And as you get more precise, you might pick up others. Sure.
You
Can I get microphone?
No, he has a question.
Oh.
Connect the question. Oh, you can ask.
Yeah, it might be more efficient to do that one first. Please.
My question is on the topic of
Louder, please.
on the topic of tidal movement.
Yes.
What exactly is the energy being transferred from the spin to the orbit?
So it's more useful to think of it not so much, energy is being transferred, but I think you can get clear intuition of it being angular momentum that's being transferred. Okay, so, suppose my host's gravitational field raises a tide on me, right? So my arms are pulled out by his intense gravitational pull. If I'm spinning, then there's a little bit of a lead on my tidal bulge here. And so the gravity that I exert back on him is a little bit misaligned from his position. And that actually puts angular momentum into his motion and causes him to move a little bit differently than it would if it were not there. So the angular momentum, I think, is a clearer way to get intuition as to how that coupling occurs. You are next, yeah.
So first of all, I know you've heard it a countless times, but thank you for the wonderful talk. Now coming to the question, suppose there are two similar GW events, and their gravitational waves superpose on the way coming to nightmare. So do we extract the two events, or do we count it as one single event?
So at the moment, they're sufficiently rare that if that were to happen, that would probably be strong evidence of a malicious deity who was messing with us, because it would be very difficult to do that. So, if they were really similar and they hit at the same time, they would actually interfere with each other. That might really complicate how you analyze it. That is one of the things that measurements with LISA are sort of expecting to need to deal with. But they're most commonly common superposed signals are just sinusoids. They're relatively easy to detangle from one another. As detectors sort of get more sensitive and they have longer bandwidths, some of the signals are going to last in band for a lot longer. And I think it will become plausible that you will have at least some they're not going to hit at precisely the same time. That truly would require a malicious deity, I think. But you may have some that overlap in the time domain. And it will be important to make sure that you can detangle one from the other. It is kind of like the problem of when you're having a conversation in a crowded room, you're trying to pay attention to two people at once. And so you can sort of do it. But what you might want to do is, record it, listen carefully to one person's voice, and then replay it and listen carefully to the other person's voice. So you might need to do sort of an analysis that works like that.
Sir,
Hi.
Until this far, what we detected from the gravitational waves coming out from transient sources, like two binary whole mergers, dwarf mergers. But what are the possibilities of getting detected those gravitational waves coming out from the stochastic sources, like domain wall collision or cosmic strings or primordial black holes?
Yeah. So in addition to the ones you mentioned, there's other ones that have long been suspected would contribute. So if you have isolated neutron stars, they might not be perfectly spherical. They might have sort of an elliptical shape, and if it's misaligned from their spin, they will be gravitational wave emitters. When a stellar core undergoes collapse and produces a supernova, it's long been thought that they may provide gravitational waves, although modeling them and trying to understand their properties is challenging because they may not be coherent. So the ones you mentioned, the couple I just mentioned here, my friends who are involved deeply in the collaboration, they can tell you about efforts to go in and measure these kind of things. Everyone is very much looking for these signals. They're listening for them, I suppose I should say. They have developed data pipelines to try to pull them out. So far, they have set upper limits on the existence of these things. In other words, in a scientific measurement, you can rarely say something's value is 0, but you can often say it is less than some value. And so, it's not necessarily the case that the number of gravitational wave pulsars is 0, but we are confident that their contribution to the data is below some kind of a threshold. The sources you mentioned, I believe, fall into the same kind of category, right? Where there have been searches, they have set limits on their things, but as I was sort of saying in answer to another thing, the things we have found to date have been the loudest things. All these other ones are just quieter, and they're harder to find. The models that describe their evolution are not as well developed as the ones that allow us to describe merging black holes and merging neutron stars. So that's where we stand.
Hello, sir.
Hi.
Sir, my question is, can gravitational observation it help other messengers or carry information of other messengers, like in case of mergers in the very dense environment, like within the accretion disk or some dense cluster, then any possibility of producing other emission like maybe neutrinos?
Absolutely, absolutely. And a topic for a different talk is where we, and some of my friends in the front row here talked about this a little bit in their talks this morning. When, the classic example of this is the merger of the two neutron stars that happened in August of 2017. And so that one, there was no neutrino signal detected from that, but people looked, right? You wanted to see if you could find something. Again, you sort of set an upper limit. It's the best that they could do on that. There was broadband electromagnetic information associated with that. And I think someone once calculated that 20% of professional astronomers on Earth participated in papers related to the study of that event. And so now you're asking about interactions with accretion disks and what they're going to have with that. That is very much for the kind of this extreme mass ratio system that I showed you a little movie of. One of the things we are thinking about is, what if there's some accreting gas when that happens? And this will interact with that gas and cause things to happen. As it turns out, there are actually events being measured right now that appear to look like essentially a very large mass ratio binary in which there's a compact object orbiting a black hole and in a very regular fashion interacting with an accretion disk and causing quasi-periodic eruptions that are visible in X-rays. So we're not 100% sure what is causing that, but the idea that it would be something that perhaps could evolve into a gravitational wave source is a very plausible description of this. So the kind of thing you're talking about is very much, I think, going to be a part of the future of this field.
I think we'll continue the questions with T. And let's give Scott a big hand.
Thank you.
Okay, so luckily